So let me repeat what we just did in our last class. We last class discussed point P point C. It can be described by the x, y, z coordinates of the point P in the Cartesian coordinate system. The Cartesian coordinate systems coordinate x, y, z, they can also be defined as functions of three variables u1, u2, u3. And this is how x, y, z can be defined as functions of three variables u1, u2, and u3. Now, if we consider that this this function is invertible, so that we can solve for u1, u2, u3 and write them again as functions of x, y, z, and we can write u1, u2, u3 as functions of x, y, z. Say the function j, the functions in the above equations, when they are assumed to be single valued and to have continuous derivatives, so that the correspondence between x, y, z and u1, u2, u3 is unique. So u1, u2, u3 we call u1, u2, u3 as the curvilinear coordinates. We call the unique set of coordinates u1, u2, u3 as the curvilinear coordinates of the point P. The example the spherical polar coordinates r theta phi is one r theta phi is one example of curvilinear coordinates. The curvilinear coordinates have a curvilinear curves, the curvilinear coordinate curves, the curvilinear coordinate surfaces have defined the way a variable u1, u2, u3, if we set each of them equal to some constants c1, c2, and c3. So u1 equal to c1, u2 equal to c2, and u3 equal to c3. They define three coordinate surfaces. And this three coordinate surfaces, when they are taken in pairs, which is pair two coordinate surfaces, they intersect along a curve. Each pair of these surfaces, they intersect along a curve, and these curves are called coordinate curves or coordinate lines. Coordinate curves or coordinate lines. So these are the coordinate curves. This is the u1 coordinate curve. This is the u2 coordinate curve. This is the u3 coordinate curve. The u1 coordinate curve intersection. The u1 coordinate curve is obtained by the intersection of u2 equal to constant surface and u3 equal to constant surface. So u2 equal to constant surface, u3 equal to constant surface, and in intersection we get the u1 curve. Similarly, from the intersection of u1 equal to c1 surface, u3 equal to c3 surface, and in intersection we get the u2 curve. And from the intersection of u1 equal to constant and u2 equal to constant, we get the u3 coordinate curve. Next, what we're going to discuss in this course is we are going to discuss only orthogonal curvilinear coordinates. So what are orthogonal curvilinear coordinates? Orthogonal curvilinear coordinates. If the coordinate surfaces, if the coordinate surfaces intersect at right angles, the curvilinear coordinate system is called orthogonal. I repeat, if the coordinate surfaces intersect at right angles somewhere intersect or the curvilinear coordinate system is called orthogonal curvilinear coordinates. The u1, u2, and u3 the U1, U2, and U3 coordinate curves of a curvilinear system coordinate system are analogous to the x, y, and z coordinate axes of a rectangular system. Stop. So I coordinates say the U1, U2, and U3 coordinate curves of a curvilinear system. Have you Sigi U1, U2, U3 curve of these two curves of a curvilinear coordinate system are analogous to the x, y, and z coordinate axes of a rectangular system. This U1, U2, U3, they are analogous to the x, y, z coordinates of a rectangular system. If the coordinate surfaces intersect at right angles, the curvilinear coordinate system is called orthogonal curvilinear coordinate system. Aduna curvilinear coordinate system U1, U2, U3 is a curvilinear coordinate system. Curvilinear this is because these three surfaces U1 equal to C1, U2 equal to C2, U3 equal to C3. These surfaces can be curved surfaces. So U1 equal to C1 surface, U2 equal to C2 surface, U3 equal to C3 surface. These surfaces can be curved surfaces. Curvilinear coordinates. U1 equal to U1 equal to C1 surface, U2 equal to C2 surface. If these two surfaces intersect at right angles, curve is right angle right angle swine U2 equal to constant hyper surface, U3 equal to constant surface right angle U1 equal to constant hyper U3 equal to constant hyper surface any right perpendicular and coordinate system orthogonal coordinate system. Orthogonal coordinate system U1, U2, U3 curves is straight line when you have a they can be curves, still be curves. Sigi surface and is orthogonal when even though these two surfaces they intersect at right angles. This curve, this U1 curve need not be a straight line. U2 curve need not be a straight line. U3 curve need not be a straight line. Aduna, this is what we mean by a curvilinear coordinate system. See, curvilinear coordinate curve surface in the intersection surface surface variable U1 constant set over U2 constant set over U3 constant set over surfaces surfaces curve curve curvilinear coordinate curves surface right angle we call that orthogonal curvilinear coordinate system. We call that system orthogonal curvilinear coordinate system. The orthogonal curvilinear coordinate system U1, U2, U3, these three coordinate curves, they are analogous to the XYZ curves of a rectangular Cartesian coordinate system. Similarly, now let us consider what do you mean by unit vectors. Let us see unit vectors. Unit vectors in curvilinear systems. Okay. Unit vectors in curvilinear systems. Unit vector Cartesian coordinate system unit vector I hat, J hat, K hat. This represent unit vectors along the x-axis, y-axis, and z-axis. Now, in the curvilinear coordinate systems with coordinate curves u1, u2, u3, what are the unit vectors? Let r vector equal to xi hat plus yj hat plus zk hat be the position vector of a point P. And recall, let r equal to x times I hat, y times j hat plus z times k hat be the position vector of a point P. Yeah, recall. What have we known? We have already known from equation 1 that x, y, and z, they can be written as functions of u1, u2, and u3. This means since r depends upon x, y, and z, x is it can be expressed as functions of u1, u2, u3. Y can also be function or expressed as functions of u1, u2, u3. Z can also be functions of z can be expressed as functions of u1, u2, u3. So this means this r can also be expressed as a function of u1, u2, and u3. Then equation 1 can be written as equation number 1 can be written as r vector. This r vector is a function of u1, u2, u3. Since x, y, z are functions of u1, u2, u3, r is also a function of u1, u2, u3. The tangent vector, the hierarchy a tangent vector a tangent vector to the u1 curve at P. Constant number u2, u3 constant number for which u2 and u3 are constant is del r by del u1. Recall del r by del u1. That we draw the curves again. u1, u2, u3. So let us draw this curve here. So this is u1 at the point P. This is u1. This is u2. And this is u3. This is the point P. So point P is the I have three curvilinear coordinate curves u1, u2, and u3. See figures only the curves surface this is the point P. These are the three curves u1, u2, u3. A tangent vector to the u1 curve at point P, where u2 and u3 are kept constant. The curve u1 have a curve. At the point P, let us draw a tangent to the u1 curve. It is this tangent. This tangent. This is the u1 curve. u2 and u3 is constant hamaga. u2, u3 is constant hamaga. When we draw a tangent vector to the u1 curve at P. And this tangent vector is given by the partial derivative of r with respect to u1, keeping u2 and u3 constant. Repeat again. A tangent vector to the u1 curve at point P is equal to P del r by del u1 P ni partial derivative of r with respect to u1 where we have kept u2 and u3 constant. So the beginning. This is the tangent vector given by this expression. Then a unit tangent vector. Tangent vector is unit t. Then a unit tangent vector. Then a unit tangent vector in this direction. Then a unit tangent vector in this direction is, so she's in a vector vector is unit vector located. You simply divide the vector by its magnitude. Vector magnitude. No, divide what do we get? We get a unit vector along that direction. So the unit tangent vector in this direction is given by E1 E1 head unit. So E1 head is equal to del r vector by del u1 divided by this is division divided by the modulus of this vector divided by the modulus of del r vector by del u1. So this is the tangent vector, and when this tangent vector is divided by its magnitude, it will give you a unit vector. And this is the unit vector along the u1 curve at the point P. Therefore, we can write del r by del u1. This can be written as some constant h1 times e1, where h1 is equal to this value. I repeat, del r by del u1 is combined EBR. This is h1 times the unit vector, where h1 is nothing but this modulus of del r vector by del u1. This is nothing but this is obtained from this expression by multiplying this left hand side by the denominator. Denominator is left hand side multiplied to denominator is h1 so we can write del r by del u1. This tangent vector can be written as h1 times e1 head. This is h1 times the unit vector along u1. Similarly, similarly, if E2 head and E3 head are unit tangent vectors, to the U2 and U3 curves at P respectively, then del r by del u2 is combined EBRS. It can be written as h2 e2, where h2 is what? h2 is the magnitude of this vector, where h2 is the magnitude of this vector. And similarly, and del r by del u3, del r by del r by del u3 is equal to h3 e3, where h3 equal to magnitude of del r by del u3. Ko aduna I amuka hairake curvilinear coordinate system the unit vector ठीक है at this point what are the unit vectors at this point ठीक है at this point the unit vector along u1 is given by del r by del u1 divided by the length of this tangent vector that will give you the unit vector. Similarly, the unit vector at this point along u2 will be given by the tangent vector here, this tangent vector, which is del r by del 2, and if you divide this tangent vector by its magnitude, you will get the unit vector e2. Similarly, at this point, what is the tangent unit vector along u3? The unit vector along u3 is the tangent to this curve at this point P. It is given by this. This is this is tangent to the u3 curve at the point P. The unit vector e3 where e3 is the tangent vector divided by h3. That will give you the e3. Now, h1, h2, h3 have quantities in there. The quantities. So the quantities h1, h2, and h3 are called scale factors. The quantity h1, h2, h3 are called scale factors. The unit vectors e1 hat, e2 hat, e3 hat are in the directions of increasing u1, u2, u3 respectively. The unit vector e1. The unit vector e1 is along the direction of increasing u1. The unit vector e2 is along the direction of increasing u2. The unit vector e3 is along the direction of increasing u3 respectively. So this is how unit vectors are defined in a curvilinear coordinate system. So curvilinear coordinate system at the point P, at this point P, the unit vectors are defined in terms of the tangent vectors at the point P, tangent to the curves. So E1 is defined as the tangent divided by its magnitude. And what is the tangent? This is the tangent to the U1 curve. So E1 is along the tangent to the U1 curve. And mathematically, what is that given by? And mathematically, that is given by del R by del U1, keeping U2 and U3 constant. So let us consider one example. And for simplicity, let us consider two dimensions. Say, let us look at two-dimensional system. This is X, this is Y. I have a point P here. And this is the line joining the origin and the point P. X, Y are the Cartesian coordinates. So let us consider the example. X, Y are the Cartesian coordinates. We can also define polar coordinates. Polar coordinates to define the way we can define polar coordinates. That is, one is phi. That is the angle measured from x-axis. This angle is phi, and the length of this line joining the origin and the point, that is given by rho. Like the r, small r represent the way, but we shall write it as rho. Rho is the length of the line joining the origin and the point. And what is pi? Pi is the angle made by the line with respect to the x-axis measured in the anti-clockwise sense. So rho phi is another coordinate system. Rho phi. XY is Cartesian coordinate system की coordinates ni. Rho phi is polar coordinate system की coordinates ni. These are nothing but these are curvilinear coordinates. XY, rho phi, these are curvilinear coordinate systems. And we know that the unit vector along x-axis is given by the vector I hat, and the unit vector along the y-axis is given by the vector j hat. Now, what is the unit vector along the variable, along the coordinate rho? What is the unit vector along the rho curve? From what we discussed, the unit vector E rho, this will be equal to del r by del rho, del r by del rho divided by the magnitude of del r by del rho. What is the direction of increasing rho when you keep pi constant? Pi is a constant. Point P. What is the direction along which rho increase? This gives you the direction along which rho increases when you keep pi constant. Direction it is nothing but that we use a different color. It is nothing but this direction. This is the direction of increasing rho when we keep pi constant. See, line angle fixed rho increase direction. It is along this direction. So it is along this direction. So this direction is the unit vector to E rho. This is the unit vector along the rho direction. What is the unit vector along the phi direction? That is del r by del phi divided by the magnitude of this, del r by del phi. And what does it mean? This means you keep rho constant and you increase phi. Direction unit vector rho constant, how you you keep the length of this line constant and you increase phi. How you rotate anti-clockwise. You rotate this line anti-clockwise, keeping the length constant. Line length fixed, you rotate phi along the direction of increasing phi. So that will be along this direction. So this is the direction along which phi increases when rho is kept constant. So this is E phi. So this is the unit vector along phi, along the phi curve, and this is the unit vector along the E rho curve. At another point, let us take another point here. Then let us join this to another point Q. Now, what is the unit vector E rho? E rho at this point. At this point, what is the unit vector E rho? At this point, the unit vector E rho is again along this line. This is E rho. And what is E phi? E phi at this point, E phi at this point will be along this line, perpendicular to E rho. This is E phi. So at this point, at the point P, E rho is along this direction. At the point Q, E rho is along that direction. So what do we conclude from this? What we can conclude is that at different points, the direction of the basis vector E rho and E phi changes. At different points, the directions of these unit vectors can change. This is unlike the case in Cartesian coordinate system. In Cartesian coordinate system, at any point, at this point, the unit vector I hat is along this direction. I hat is always along this direction, and J hat is always along this direction. So I hat is along this direction, J hat is along this direction. This is I hat, this is J hat. So in Cartesian coordinate systems, the I hat always points along the same direction. So this is from the, and the J hat also points along the same direction at all points. This is Batakta. In Cartesian coordinate systems, the directions of the unit vector does not change. But in curvilinear coordinate system, the direction of the unit vectors they change. Okay, so what can we see from this picture? From this picture, we can see that the Cartesian coordinate systems x, y, to d, at every point, the I hat and the J hat, they always point along the same direction. I hat direction, they always along the right. J hat direction now always upwards. But for the rho phi coordinate system, at different points, the unit vectors E rho and E phi they change. Okay. So as another homework, I want you to draw the curves. Draw the curves. Number one, rho equal to constant C1. Number two, phi equal to constant C2. This is C1, this is C2. Say the equina in 3 dimensions. When I put one of the coordinates equal to a constant, we get a surface. But in 2 dimensions, here we are considering only two dimensions. In 2 dimensions, when I put one of the coordinates as a constant, what do we get? We get curves, not surfaces. Surface function curves and we get curves. So what you have to do at your home, rho equal to constant. Rho equal to constant over curve say. Rho equal to constant curve to ye or phi equal to constant curve to ye over. Yarba. Aduga sigi curvilinear coordinates concept say clear in 3 dimensions, draw the surfaces. Spherical coordinates. In 3 dimensions, for spherical coordinates, draw the surfaces. Number 1 are equal to constant. Surface number 2, theta equal to constant. Constant number 3, pi equal to constant. Pi equal to constant surface. CVZ, you the homework door. 2 dimensions curve sarani, rho equal to constant, phi equal to constant curve to your. In 3 dimensions rho the surfaces are equal to some constant C1, phi equal to some constant C2, constant C2. Sorry, theta equal to some constant C2, phi equal to some constant C3. When you draw these surfaces, curves, you will understand the curvilinear coordinates better. I think we can stop for today here.